Hey guys, so in this video I'll be telling about Metropolis algorithm. It's a really simple thing to understand. Okay, so I'll be explaining it. And so let's begin with simulating a coin toss. If I ask you to simulate a coin toss such that the probability of heads is 1 by 2 and probability of tails is 1 by 2. I ask you to simulate it in a computer. How will you do it? You can't just say to a computer that the probability of heads is 1 by 2 and of tails it's 1 by 2. So basically what you do is you make a candidate array. Okay, candidate array. The spelling is wrong. It's not like I don't know it, but yeah. Anyways, yeah. So this I make a candidate array such that it has one heads or one tails, and I use rand function on it. Okay, so computer chooses one among these randomly, and that does the job for me to simulate a coin toss. Okay, so depending on how good random function is, this will be a really good simulation of a perfectly random coin toss. Okay, so basically I make a candidate array of two elements containing heads, one as heads and one as tails, and I say computer to choose randomly between any one of the elements. Okay, so now imagine if I want to simulate a coin toss such that my probability of heads is 2 by 3 and probability of tails is 1 by 3. Okay, so now it's a biased coin toss now. It's not the same as this, so you cannot choose a candidate array to be this, because of course that corresponds to 1 by 2 and 1 by 2. So basically what you do now is you take this as your array, or maybe you can take heads, tails, or tails, heads, doesn't matter. You also can take tails and heads, and then you apply rand function on this. Okay, and say computer to choose randomly one among these. So this will do a perfectly good job of simulating such a system that heads occurs 2 by 3 times, 2/3 of the time, and tails occurs 1/3 of the time. Okay, so this was really easy. Okay, because you know the probability already, and it was really easy. There were only two discrete outcomes. Now imagine if I say instead of heads and tails, there are n discrete outcomes. Okay, so 0 to xn, and this is the probability density. Okay, not probability probability, but the probability density curve of all these events. Okay, so now how will you simulate? How will you ask computers to simulate this? Okay, because each point has a probability of 0. It's basically like a dartboard where each individual point has 0 probability of the dart has 0 probability of landing on each individual point, but it can land in some area. Okay, so basically you can define probability for some range. Okay, so yeah, so I want my computer to simulate this distribution. By the way, just randomly, I want to tell you about the probability density curve of heads and tails. Okay, so this is one way I can think of to make it. This is 0.5, this is 1, and this is 1. Okay, so basically all these points that lie in the range of 0 to 0.5 represent tails, and all the points between 0.5 to 1 represent heads. Okay, and these represent tails. So basically the probability of occurrence of tails is 0.5 and heads is 0.5. Okay, so this is just one way to represent the probability density. And if other way I could do is I could take this as 0.5 and make this as 1 and make this as 2. Okay, so yeah, I just wanted to inform you about this. Doesn't matter, not important actually. Yeah, so basically how will I simulate this? What I do is I take this curve. I'm just making this again. Okay, oh, it's really different from this one, but yeah, again, it doesn't matter. So I take some random point xi. Okay, now try to understand the probability of the points in the neighborhood of xi is nothing but pxi dx. This is the probability of occurrence of the points in the neighborhood of xi. What I do is I take a range, okay, which belongs to minus delta to plus delta. Now what I do is I take a new point, x new is equals to p. Sorry, yeah, my bad. Yeah, so now I take a range which is randomly selected, which randomly selects a point between xi minus delta to xi plus delta. Okay, now this is xi plus delta, this is xi minus delta. Now if x new, if this is the probability of occurrence of points in the neighborhood of x new dx. Okay, if I divide it by p xi dx, now if this quantity is greater than 1, what does it imply? Basically, it implies that the probability of occurrence of points in the neighborhood of x new is more likely than xi. So since I begin with xi, I put xi in my candidate table. Now if this is valid, I will add x new here in my candidate table. Okay, I will add it in my candidate table because it is more likely than xi, and I will repeat the process again. What I'll do is, now my x new will be xi. Okay, x new will be xi, x new yeah, so I will update xi to be my x new, and I will again repeat this process. But now what if this is less than 1? What if this is less than 1? Okay, what if this is less than 1? Okay, that would imply this would imply the fact that xi, probability of occurrence of points in the neighborhood of xi, is more likely than the probability of occurrence of points in the x new. So instead of, in this case, what I'll do is, I'll take this to be my candidate table xi, and I again add xi here. I don't put x new here because xi is more has a probability of higher occurrence than x new. Get it? So I add xi here. So I keep repeating this process. Okay. Now the thing is, even if the probability is less than 1, so even if pxi dx px new dx, let's say it is 0.8. Okay. Now this doesn't imply the fact that this will never occur. Okay. Of course, it will occur less than xi, but does it imply that you shouldn't have it in a candidate table? No, right? Because it can still occur. Let me try to give you an analogy. Okay. So, yeah, basically we can take this only. Imagine if you have a biased coin such that probability of heads is 9 by 10 and probability of tails is 1 by 10. Does that mean you will not have tails in your candidate table at all? You will have it, right? You will have 1 tails and 9 heads. Okay. So yeah, similarly here you still add x new to your candidate table. So basically this is our final result. If this ratio lies in the range, it is greater than 1, I always add it in the candidate table, and I will let's take this as gamma. Okay, now gamma will depend on question to question. Okay, so but for for some generalization, I'll take gamma as, let's say, 0.7 to 0.8. Okay, so this is my gamma. Oh, I just wrote delta and I'm calling it gamma, my bad. Yeah, this is gamma. Yeah, sorry, that was a blunder on my part. So yeah, basically if this ratio dx gets cut, so it doesn't matter. If this ratio lies in this range, no, then what we do is we add x new, we keep adding x new to our candidate table, and we keep repeating this process again and again. Okay, so eventually what you get is a candidate array which kind of simulates such a probability distribution. Get it? So what else can I say about it? Basically, this is an arbitrary value which depends on question to question. Okay, so basically I hope you get the meaning behind when to add that x new and when not to add x new. Okay, and this delta is also arbitrary. arbitrary. Okay. Now, in this case, xi minus delta would definitely get added to my candidate table because it is clearly more probable than xi, and this will also get added to my candidate array. Okay, I'm calling array stable. I don't know why, but anyways, yeah. So this would also get added to my candidate array. But if this was the point, xi plus delta, I would take delta really large, then this would be my xi plus delta. Then this wouldn't get added to my candidate array because it has a really less probability of occurring when compared to xi. Okay.